My name is Dave Dornfeld. I'm Associate Dean for Interdisciplinary Studies, and it's my pleasure to serve as the introducer tonight for this innovation lecture series. I work with Dr. Sidhu in the Entrepreneurship and Technology program. We have a real special innovator with us tonight. I'm going to read a couple of things from a formal background. He's going to talk a bit about it, and then I'm going to read a paragraph from an article that was written in 1998 that gives you a little better sense of his background. Our speaker tonight is Jerry Fiddler. He founded Wind River Systems, a device software optimization embedded software company, in 1983 after working on it in his garage for 2 years. He was the company's CEO and chairman for 23 years, now boasts over nearly $300 million in revenues and more than 1,000 employees, according to Wikipedia, and we know that's always the truth. Market cap is over $1 billion. Currently chairman of Solazyme, a biotech company working with algae for energy, industrial, and health applications. He was also in the real-time systems group at Lawrence Berkeley National Laboratory up on the hill prior to founding Wind River. He has degrees in music and photography, as well as an MS in computer science from the University of Illinois. There's an article when I Googled Mr. Fiddler in something called EE Times from 1998, and there's a paragraph I just want to read that gives a little background on how he got from Illinois, in the heart of the Midwest, not a red state, but sort of a purple state, to California. In 1974, after graduation from the University of Illinois with a double major in music and photographer, Fiddler's direction seemed pretty well set. But while playing electric guitar in a fusion band called Afterbirth, he saw a job offer as a resident composer for the University of Illinois' dance department, a gig he really wanted. To be eligible, he needed to go back to school, and he did, choosing to get a master's in computer science because, quote, it looked interesting and coincided with an interest in computer-generated music. In '77, he gave up the idea of being a professional musician. He was living in Urbana, playing guitar in another band called Random in search of a new direction for his life. He found it in a paper on voluntary simplicity out of Stanford Research Institute in Menlo Park. Aha, Fiddler thought, a think tank. I think I'll go there and look for a job. So he hopped in his '65 Dodge pop-top van and drove to California. There was nothing available at SRI, but a bulletin board there directed Fiddler to the University of California's Lawrence Berkeley Laboratory, which needed someone with both a humanities background and computer science know-how to build human interfaces to big systems. The rest, as they say, is history, and he'll provide some of that history. So let me introduce Jerry Fiddler.
Thank you. We've covered this slide. My background was pretty varied. By the time I got to my double major in music and photography, I'd been through several other majors, chemistry, geology, there's another one, I forget. And what was happening about that time was that microprocessors were coming around, and the nature of what a computer was and what it could do was really changing. It was just an unbelievably exciting time if you had any interest at all in technology, which even as a musician I did. So I did that. I switched to computer science. To my great amazement, they let me in the grad school, came out here to Lawrence Berkeley Lab, and then began Wind River in 1981. I was frustrated with government work for various reasons, and I really didn't do this to start a big company or to make a lot of money or anything like that. Really what I was looking for was freedom. I was looking for flexibility. I thought that if I started my own company, I'd be in control of my own time, which I was as long as it was always. And so I was there until 2004. I was either CEO or chairman for 23 years. Long way. What I'm doing now, so I left there several years ago. I'm on half a dozen corporate boards. I'm still on Wind River, and then the others are all private companies. You may recognize some of the names, as well as a lot of nonprofit and advisory kind of boards. I'm chairman of Solazyme, which is the biotech that you just heard mentioned, and I'm going to talk some about a couple of these companies. And then I spend some time here at the university. And actually, the last bullet is wrong. I forgot to delete it, but I was CEO of Chabot Space and Science Center until a couple months ago. So what I want to start, oops, got to get used to the right way. I want to start by talking about my master's thesis. This is what I did back in grad school, and I didn't do what most people do, which is go find a project and see if somebody will take you onto the project. There was something I really wanted to do, and that was to build a little portable computer. So I did, and it was called the Tweed, the Text Wizard electronic editing device. You'll see why in a moment. It was called the Tweed, and I envisioned this thing being for like a journalist who could like edit up a little. At that time, of course, somebody who was in the field would call on the phone and they'd dictate their story in, and I thought, well, that's kind of silly. They could put it in a little text editor and shoot it across a modem at 300 baud. But they could have done it. So I decided to build this, and I think that it was the world's first portable computer or terminal, depending on how you look at it. There it is. This Tweed suitcase cost me $1.50 at Salvation Army, so I didn't mind cutting holes in it. That's what's inside it. Here's a board and a power supply, and you can see wiring and stuff. Unfortunately, the keyboard is lost. There was a keyboard that clipped in there, and it was totally weird keyboard. That's what it looked like. It was wire wrapped. I did about half of the I did about half the wire wrapping, and I got a friend to do another half. This it was another musician, and he really wanted to learn how to do computers. So I said, "This is how you start. You wire wrap." So I taught him how to wire wrap, and he did about half of this in return for free beer, which I later learned it would have been much better to provide the free beer after he was done, because it was a big debugging job. That's the microprocessor. It's an 8080, which is an 8-bit microprocessor, one of the early ones, and yet I couldn't afford it, so that's a freebie. You can see it says sample. And then there's a clock up there. This is the memory. This is 4 EEPROMs, programmable read-only memories. These are 4K each. So that was the entire program memory for it. How I developed this thing was pretty interesting. By the way, you might want to look at this all and think of the projects you're working on right now. I got to tell you, when I did this, which wasn't that long ago, seems like yesterday in terms of my lifespan, this seemed really state of the art. This was like high tech. People would come in and say, "Ooh, that's so cool." And you look at it now, and you look how far things have gone, and think about what you're doing now. Think what they're going to look like in 20 or 30 or 40 years, and think what you're going to be doing then. It's going to be very different. So what did I do? I designed the hardware. Wire wrapped it, and then I started working seemingly forever in actually making this thing work. So what I did is I wrote some software in a program called PLM. It's an old language, and then I'd compile that and I'd make a hex listing on paper of the program. I'd actually type it all into hex, and then I'd have to go to another building with this listing and go to a PROM programmer and key in all the hex into this PROM programmer and program the ROMs, and then walk over and stick it into my little computer and then debug it with an oscilloscope. And when it didn't work, I'd have to go through that whole cycle again. Incredibly painful, and yet the amazing thing is I actually did it, and this thing actually works. So that thing you just saw actually became, I think it was the world's first portable computer. Nobody's ever showed me an older one. But it gave me a good sense of the wrong way to build a system, and yet at the time it was the only way to do it. So what I didn't quite know what to talk about today. I didn't want to stand here for a half hour and talk about myself. So what I decided to do is talk about innovation, since that's the name of the series. So what I want to talk about is 3 innovation stories. I want to talk about VxWorks, which is the product that got Wind River off the ground, and Crossbow, which is a company that some of you may know because it's spun out of Berkeley, and Solazyme, which is the company that I'm working with now. First let me tell you about Wind River a little bit. That's the company that I started and ran for a long time. Wind River does device software management. It means we do the operating system and the application and middleware that controls devices. And it's in all kinds of devices. I wrote here many millions, but it's certainly in hundreds of millions, and it may be in 1 billion devices. And it's in all of the kinds of things you see here, all throughout the communications grid. If you make a phone call, your voice is certainly going through Wind River software somewhere. It's in a lot of handsets. It's in robots, including that cool Honda Ashimo robot that you see on TV. It's the operating system for the Mars rovers. All the little things crawling around up on Mars run a Wind River operating system called VxWorks, which is the one I'll talk about. It's in digital cameras and printers and car nav systems, and it controls anti-lock brakes in cars. Anytime something's embedded, there's a good chance it's running a Wind River operating system, probably VxWorks. I gotta stop doing that. Company started in 1981. I began it. It was a sole proprietorship. It was in my garage, the one you see right there. It was a one-car garage, not even a big one. And so started there, moved in about, the early customers, we were doing consulting. So what we were doing was projects for other people. Somebody would come, say, I got to build this thing, can you help me do it? And it was all real-time stuff. I'd been in the real-time systems group at Lawrence Berkeley Lab, and I'd done some things, particularly around human interface, using touch panels. We had one of the very first touch panels up there. And I'd done a lot of work around software architecture for that. So people would find me after some papers I'd written and things. And so I started working with things mostly around video, because that's who found me first. So I did a video editor that's used by Francis Coppola. I still work with him a little bit. Got used by National Football League teams for editing game films. So started doing this consulting, incorporated in '83. In '87, started selling a product, and that's what I'm going to talk about in a minute, called VxWorks. And then things started to grow very quickly, went public in 1993. I stopped being the CEO in 1994, but stayed chairman. In '97, we became the first operating system on another planet. Wind River still owns 100% of the Martian market. Then things started to really go crazy in '99, but I don't want to talk about that because that would take too long. So go back to 1985 to '87. So this was a time Wind River is doing consulting. We're doing things for other people, and we're building embedded devices, and the process by which we're doing it is extremely painful. I'll talk, it's not much different. It's better than what I did on my Tweed, but it's not a lot better. And now microprocessors are starting to change. New microprocessors are coming around. They're 16-bit instead of 8-bit. These are the 68,000s and such that were around then. And they were actually able to replace things like mini computers. They were actually able to do really good, important jobs, but the software sucked. The software was terrible. There was no good software for us. So we started by actually buying a little bit of software. It was called a kernel, and quickly found out that it didn't work. So we needed to start improving it for our own use. So the reason for that is that most people who were doing this kind of work really weren't software people. The most embedded software at that time was written by hardware folks, because it seemed like the hard part of this job was you make the hardware work and then you sling a few lines of code and you're done. But now with this change in microprocessors, it was going the other way, and the software was much harder to do than the hardware, but there were still no good tools to do it. So we brought a really different perspective. So that's what's going on the embedded side. There's also all of this really exciting stuff going on the computer side. You've got the Ethernet, not really the internet as we think about it yet, but Ethernet was around, which is a fast network. So you could at least do real nice local area networks. Sun was building what were called diskless workstations, because at that time disks were really expensive. So it was thought that the best way to do this was to have no disk in your workstation so everybody could share a disk. Seems really lame now, but in fact that's where a lot of this networking technology got built up around. And so there was all of this stuff going on around the network, and as software people, we really saw that. Where most people working on embedded systems didn't. And so we had a really different idea on how to do this, and so we took off and did it. So, this is what we did. This is the way embedded systems were built back then. You had a computer up there, and you had an embedded thing that you were trying to build. This modeled whatever the device was that you were trying to build, and you connected them with a serial line. And you downloaded, you built your whole image, you did the compiling and everything, and you downloaded it across the serial line, which was very slow and very error prone. It would often take you 20 minutes to an hour just to download the image. And then once it was there, you couldn't interact with it very much. So it was a really primitive way to debug any software. And then the software that you had here was very little. You didn't have file systems or networks or any of the things that we today think of as what you need to do that. So we looked at this and said, we just can't do the stuff we need to do, because we were building complicated systems. We were building a filmmaker's workbench for Francis Coppola, and we were building pretty complicated things, and we just couldn't do it this way. So we said, we see another way, and it's this. It's a network. So we just took an Ethernet, and then you could take a couple of embedded systems and some computers, and you attach them all to the network, and now you've got a 10 megabit thing. So you're up 2 or 3 orders of magnitude faster, And now what we put in here was stuff like remote files and incremental download, and you could interact. We put a shell there so you could interact with it. None of this stuff seems like rocket science, but nobody had ever thought of doing it this way before. So what we did was we took stuff that was already quite common in the computing world and moved that to the embedded systems world, these devices, which nobody had ever done, and it worked. And it was great. It went fast and it worked great. And the way we did it was basically two engineers, myself and Dave Wilner, a Cal grad. And we did it for our own use because we needed it. We didn't build it as a product. We built it as something that we needed to do the work we were doing, although we always thought that maybe we'd productize it. And so we wound up doing that later. And we did it by using as much existing code as we could find. We used a Sun C compiler, and we used, we got TCP/IP from Berkeley. By the way, we were actually the first people to ever use TCP/IP, the network stack from Berkeley, which is now free and used by everybody in the world. At that time, you couldn't license it because it was locked up in this weird license with AT&T, and we're actually the ones who worked with Berkeley to get it shaken loose. And so we took all these pieces, and we wrote as little as we possibly could, but we figured how to take all these pieces and make them work together, and it enabled two people to come out with this really different product, this really different way of doing things than anybody had ever done before. We made it all sing together, and we did it because we knew the problem really well. We'd been living with the problem, and we knew we had to solve it, and we brought a really different perspective. We brought this computing and software and networking perspective to embedded systems, and the result was that when we would show this to somebody, when we turned it into a product and show it to somebody, their jaws would drop. Nobody had ever imagined that they could build a system like this, that they could work in this way, and something like 80% of the people we showed it to wound up buying it. It was just an incredible ratio of who we sold it to. We also found that that network, which remember we put this network in because it was going to help us download software and debug it, actually turned out to be really important to the products people were building, and nobody had ever even thought about it. Nobody had ever thought I could have a network in my device, but once we put it there, they didn't take it out, and then that locked them into this way of working. And it enabled us to re-engineer the business from a consulting company because the competition was way behind. It took 5 to 7 years or more before the competition caught up to anything like this. And the tangible result was, this is revenue. Now this is a log graph, because if you didn't do it as a log graph, it would just be crazy. But you can see we grew over 100% a year for 5 years as a result of innovation that was done by two guys because we needed it. Now, it grew a lot by then, and I don't mean to imply that there wasn't a lot more work and a lot of stumbling blocks along the way, but the innovation that made it happen was Dave and me in a lab coming up with a new way to do something. This is Wind River today. Actually, this is half of Wind River today. We're actually in 4 buildings over in Alameda, S&P mid-cap 4. But it came from that spark. It came from a couple guys at a lab. So I'm going to talk about 2 more innovation stories. This is Crossbow. Crossbow, a lot of you may know it because they do wireless networking. They build the moats that are used by, by a lot of wireless networking, wireless sensing network people here. But they also have another part of the business, which is inertial sensing, and this is what I want to talk about. Crossbow started here at Berkeley, and it was Mike Horton, who was a student, and Richard Newton when this was before he was dean. He was still a professor at the time. And so it was Mike's graduate project here at Cal. And at the time what was happening was there was, MEMS was coming around. MEMS are, probably most of you know, but they're little etched, basically machines. They're made like a chip, but they act kind of like a machine. And they're cheap. But the only MEMS device, and everybody was talking about them, but there was only one MEMS device that you could actually buy that wasn't ridiculously expensive because it was made in mass quantity, and it was an accelerometer. It was used in airbags in a car. And so that's what, when your car stops, that's what triggers the airbag. And so they were cheap, but they were also incredibly inaccurate. Basically what it could tell you is we're about to crash and we're decelerating at 5 Gs or something. It couldn't really tell you any more than that. But Mike and Richard thought, what if we couple this with a DSP and try to really understand what it's doing? And they found that if they took this real cheap MEMS device and coupled it with a signal processing chip, they could actually get pretty good results. And so they could use it to be a pretty good accelerometer, and then by combining them, by combining several of them, you could make kind of a gyroscope. You could make something like a gyroscope. Now, a gyroscope is an expensive device. They're not always expensive, but in terms of dollars, but they're expensive in other ways. They use a lot of power. They fail very quickly. Some gyros have a mean time between failure of 1,000 or 2,000 hours. As a pilot, I'm a private pilot, and one of the things you learn almost immediately when you get in a cockpit is how to fly when you lose all your instruments, because sure as hell, one day your gyro's going to go out. They just break. And so it scares pilots to death, but it happens. So what they thought is we could replace these, and so very cheaply, they could build something that was a better gyro. It had a much longer lifetime. You didn't need a vacuum system to drive it. In airplanes, at least, there's actually a vacuum system to drive the gyro. Lower power, lighter weight, cheaper to build, which for a company means higher margin because you can still sell it for a lot of money. And they could also build other things. They could build accelerometers and these other parts. The initial things they built were not very accurate. They were not as good as most gyroscopes by most common measures, but they were good enough for a lot of applications, and they had these incredible advantages that I just told you about. And the thing is that they could improve, they could only get better because the MEMS parts would get better and DSPs would get more powerful and their algorithms would get better, and they knew they'd only get better over time, and now they're building systems. So some of them include GPS and other sorts of stuff. And they managed to build a really nice business around this. So what they did was they looked at these MEMS devices, which are just becoming available, and they brought a really different perspective to it. Again, it was a very small group of people. The initial work was done by Richard Newton and Mike Horton, and then they had a very small team. Crossbow today is something that they're still a young company. It's still private, but they're, I asked Mike what I could say. So it's more than 20 million. I can't tell you how much more. But they're building some really cool things. They're doing things, this is a precision agriculture. They've actually changed the way a lot of agriculture is done. This was the first airplane to ever fly around the world nonstop, and that has a Crossbow inertial in it. And now they've got a couple of really big deals. This is the Eclipse business jet, and Crossbow replaces all of the gyros and basically all the, not the actual glass cockpit, but all of the instruments, the sensor part of the instruments for the Eclipse, which is just coming out now. And now they're moving upstream, and they're actually building the whole thing. So this is a device that's going to be sold under the name Bendix King, but it's actually built by Crossbow. And so they're building the display and all of the software and building the entire instrument. And they still do the wireless sensors as well. So they still have the wireless side of the business. But they've been able to take this, again, a very small team, simple innovation, a couple guys, and turn it into what looks like it's going to be a really interesting business. So let me talk about one more. This is Solazyme. This is the company that I'm spending the most time in now. I'm chairman of this company, and they're working with algae. These are all different algae. Algae are really interesting. They've been around, so over half the world's biomass is algae. It's everywhere and always has been. There's over 100,000 known species, and we're discovering them just in our lab. We're discovering species all the time. They're the oldest plant life. They've been around for 3.5 billion years. Now, if you can think about how much change the Earth has gone through in the last 3.5 billion years, how much the sunlight and the composition of the sea and of the air and the temperature and everything else has changed, and these organisms have been able to adapt to all of that. And what they've done is they've built up some quite amazing mechanisms for what they can do in order to protect themselves from, and even today they don't have any control. They're little floating things, so it can be bright sunlight, it can be dark, it can be hot, it can be cold. And so, for instance, they make a really interesting molecule to protect itself from sun damage when it gets too bright. So they're very interesting. They're adapted well to all sorts of places. It's a complete photosynthetic organism. It does everything any plant does. They're much more complex than bacteria are, and most biotech is done with bacteria. So Solazyme started when there were two guys. Again, there's that magic number of 2. And they looked at the landscape. In 2001 or so, they started on this, and they said, these are really interesting organisms. Nobody's really worked with them. Why not? Because all the money that's gone into biotech has gone into one of two things, either agriculture, making better corn, or pharma, and all pharma is done either with E. coli, which are a bacteria cell, or with CHO cells, which stands for Chinese hamster ovary cells, which are used for, sometimes they need, anyway, that's where all the money has gone. No money has gone into algae. They're harder to work with. They've got, because it's a much more complex organism than a bacteria, so they are harder to work with. But now, and the people who I talked to about this, they study. They don't. So I talked to botanists. So let me skip forward a minute. It turns out that there's an algae species that exhales hydrogen. It makes hydrogen. Now it doesn't make very much. It doesn't do it in a very commercially useful way. And Solazyme actually started around that organism, thinking, well, what if we re-engineer this thing to make a lot of hydrogen? That would be cool. But when I started calling, my first reaction was, well, if it's there, why hasn't anybody tried to do this? And the reason was, I would call and I would talk to specialists in algae. I'd talk to a botanist, and he'd say, oh yeah, we know, and this makes hydrogen, and isn't it interesting what that tells us about photosynthesis? But none of these guys were saying, well, what if we can make a lot of hydrogen? Because it was just sort of an interesting fact to them. So, and there was also this emerging toolkit. People were getting better at learning how to do bioengineering and insert genes and all of that. And new energy sources are needed. So they put all this together and said, let's start a company around making an algae, getting an algae to make a lot of hydrogen. So what they did, the two founders set up a lab. They started on very minimal resources, 150 grand. They hit eBay. It turned out that there were a lot of biotech companies that were going bust at the time, so you could get gene splicing and all the equipment you needed for pennies on the dollar on eBay, and they did. Set it up in a little warehouse. They added 2 more scientists, and they started playing with algae. And they developed a new tool set. They developed ways to insert genes into algae. They developed new ways to grow it. They developed new growth media for it. They developed all of the things you need to really work with these organisms. And they put together a really sophisticated business model around hydrogen, around how would you make this work with hydrogen. And what they realized by building this really sophisticated business model is it wasn't going to work. We thought we could make the organism, but we couldn't. There was no way to store it. There was no way to transport it. The business model wasn't there. So they very quickly said, we can't go there. Let's do something else. But now we had this really nice toolkit. We had ways to work with the algae. We knew a lot about it. We had a team. We had a lab. So what could we do with that? Well, algae are really good at other things, so they started moving towards some health and wellness products, some skin cream, and some other stuff, which, you can build a nice business out of it. I wasn't completely excited about it, but there you are, so you do what you need to do. Then they came back and started working on some other ideas, and they came back to energy again. So where they are now is this. They're actually pursuing 2 different product lines. One of them is some health and wellness products, skin cream and stuff you eat that makes you healthy, and I won't talk much about that. And the other is energy and industrial. So they've got some industrial lubricant there, and they're making oil. We're actually growing oil. They're pretty well financed. Actually, it was just announced today. Solazyme just earned their first grant. We were awarded a $2 million ATP grant this morning. Go ATP. This was actually, Bush has been trying to kill the ATP program for the last 6 years, and he's finally succeeded in killing it. So it's gone. This is the very last round of ATP grants that'll ever happen, and we got really lucky and got $2 million in the last round. We've got over 25 patents filed. I think there might be 2 issued now. And the thing is that this company is now able to produce thousands of gallons of biodiesel today. And there's nobody else who can do this. You'll start to hear about people making biodiesel or oil from algae. There's nobody else who can fill a hypodermic syringe with the stuff. There's nobody else who can make 10 cc's of it. And this company, Solazyme, can make thousands of gallons of it today. Nobody else can do that. And then there's also they're very close to a product in health and wellness. So let me talk about biofuels for a minute. Biofuels today come from, you hear people talk about a couple. You hear people talk about ethanol and about plant-based biodiesel, which is biodiesel made from corn. Both of those have real problems. Plant-based biodiesel is a problem because you can't grow enough corn, and food prices are already going up because the corn's going into other things. Ethanol is a problem because cars don't run on it. You got to convert cars, you got to convert gas stations. You can't put it in a pipeline. It's tough to transport. It's tough to store. It's really not a very good fuel. Estimates are that it could cost $1 trillion to retrofit the infrastructure so that everything runs on ethanol, and that's just not going to happen. So there's some things in the future, and so you hear about these various things: algal, biodiesel, renewable diesel, and actually jet fuel and butanol, which is an alcohol. This is what we think what Amyris is working on, Jay Kiesling's company. So what we can do is we can actually make biofuels that are completely compatible with everything that's out there. It makes, we can make a biodiesel that you could put in any diesel car. My wife just got a diesel car a week ago, and I promised her that it'll be the first car on the planet to actually run on algal biodiesel. And the other thing we're making, which nobody else is even talking about, is a biocrude. Basically, we can grow oil. Back in grade school, you all learned that oil that's in the ground came from ferns and dinosaur bones. That was a lie. It came from algae. And the algae that made that oil can still make it. The problem is they make it very, very slowly. But we think we can get it to make that oil much faster. So we're actually working on, in addition to diesel, we're working on oil that you can just take up to the refinery in Richmond and turn it into jet fuel or plastic or whatever else you want. The cool thing about this is it's a very low carbon footprint because it still burns carbon. When you put biodiesel in your car and you drive around, you're still putting carbon in the atmosphere. But the thing here is that you're also taking the carbon back out of the atmosphere. All the carbon you're putting in is also being taken back out. And so we're using this. We can make diesel. We can make gasoline. We can make jet fuel. And so that's where the company is right now. I won't go through all the advantages, but it's great stuff. Again, it's a very small team, and what they did was they brought a biotech perspective to a very different organism. It turns out algae is really different than E. coli and the other things people had worked with. So they brought a really different perspective to this. They tried lots of ideas. The first one didn't work, but they built some tools. They were the users, and they're in pretty good shape. One of the things I've learned out of this, by the way, is that biology and engineering are really different. In engineering, you decide to build something, and you know what you're trying to build, and you start from the beginning, and you get to the end, and so you've got some intentional outcome. You know what you're trying to get to, and you've got a designer who knows everything, hopefully, that's needed to get there and all of that. Biology is quite different than that. In biology, the only goal is reproduction. That's what an organism needs to do. It needs to reproduce. There really is no end, and it's hard to know what the beginning ever was because it evolved from something else. And the way it works is it makes billions and sees what survives and reproduces. So it's a very different thing, and biotech, which is what Solazyme is, combines these two things. And so it's a really interesting process. I've learned a lot by being there. By the way, this is also coming back to engineering. So in the same way you can combine these things and do biotech, you can also start to do genetic algorithms. This is a cool little antenna that was evolved online. This is a genetic algorithm that created a very, very good miniature antenna that no human being ever would have designed by going through this random mutation process. So what you got here is you've got 3 innovation stories. They're all companies I've been part of, so I know them all well. One's software, one's hardware, one's biology. One's in the 80s, one's in the 90s, one is quite recent. But there's all of this stuff in common. They're small teams. In fact, I think they were all 2 people. Or around 2 people. They all took existing elements and put them together in different ways and brought new thinking to technology that was already there rather than trying to do too much all at once. And they all required new skill sets to build. One of the things I think so this is real discontinuous innovation. Discontinuous innovation, right? It's not just, well, one step past the last thing. It's a real change. It's a non-differentiable point on the curve. And I think it's very hard to do in big companies. I think it almost always comes out of small teams and new companies. There's a book about this, which I'm running out of time, so I won't talk about much. There's a wonderful book, which I highly recommend, The Innovator's Dilemma by Christensen, and he talks about this as disruptive technology. It often happens in a user-driven way. At Wind River, we were the users, right? We knew what we needed. We knew what we wanted to do. We brought some different perspective to it, and we did it. At Solazyme, we were the users of the tools. We built the tools. Even though the original business ideas and where it went, it evolved. It went somewhere else, but we were the users. One of the things I think is interesting is this is how open source works. In open source, the users write the software. So there's really different kinds of innovation. And there's people who innovate around business models, around new pricing, new distribution, what are called roll-ups, which is combining things together. There's incremental distribution. I think this usually happens most successfully in companies. And then there's these discontinuous things. And I think they're almost always done by startups. They're almost always done by a few people. It's risky and it's really exciting. And honestly, it's the only one of those that really interests me very much. I don't do anything with the others much. So this is what I'm doing. And I'm happy to answer any questions you've got. Talk about anything. Yeah.
I'm wondering, when you're up at LBL and you decided, you wanted something that's going to give you a little more freedom, how did you find your initial clients, or how did you convince them that, you were the right person to do this, and what did it take to really build that initial client?
Can everybody hear the question, or do I need to repeat it? The question is, when I was up at LBL and decided to go off on my own, how did I find my initial clients? I'd written some papers, so I have my name on some things, and so I actually got a call, and I just decided to do it. I still had to sell the client, my first prospective client. Actually, the first one I tried to sell was a deal to redesign the ride control system for Disney, and so I actually designed and wrote a proposal for how to build a new control system to control, Pirates of the Caribbean and all the stuff down at Disney. And Disney wound up rejecting that and going with a different bid. But this was the second one I did, and it was a question of being professional. I bought a laser printer, which, at the time, people were using typewriters, and proposals were, typewritten and stapled. And when you gave somebody something that was laser printed and that looked like it had been typeset, it was extremely impressive. It almost didn't really matter what the proposal said. So I started to pay attention to things like that, and I got the first client. They wanted to hire me as an employee, and I just said, no, I'm not interested. I think I'd like to do this as a consultant, and they agreed to it. Once I had done one job, well, actually what happened was interesting. So I took this job. It was working for a company called Control Video, and I did it for a few months, and then two things, I guess, happened the same day. I got evicted, which meant that I had no place to live and no place to work because the business was in the garage. And my wife, she was my girlfriend at the time, got laid off because she was a teacher, and teachers get laid off a lot. So I thought, well, what are we going to do now? We went out to dinner, and she said, why don't we go traveling? And I said, oh, okay. And so I racked my brain and said, is there anybody who could take this over for me for a few months? And there was only really one guy I could think of. It was a guy named Dave Wilner, who was up at Lawrence Berkeley Lab at the time. And I called Dave and said, you want to take this over? And he said yes. And so he came on as really an employee, took over this one job I had, this one consulting job, went away we traveled for about a year, traveled around the world, came back, and we turned it into a partnership. But that's how, once we had one client, getting more clients was never a problem. Now this was consulting. It's different than if we had started by building a product and then went out in sales mode to try to sell, would you please buy my product? I think that would have been way harder. But consulting, once I had the expertise and once I could demonstrate it, getting new consulting clients was not difficult. And I think it's a great way to start a business because you're actually doing something, you're generating revenue, you don't need to go out and get venture capital, you don't have that kind of time pressure because you've got something you're doing that's paying the bills while you figure out what it is you really want to make if in fact you don't want to do this on a permanent basis. Yeah.
So Solazyme, Wind River, and Crossbow are all completely different areas of engineering. So
Right.
How did you know that you had enough knowledge in each of those areas to become more involved?
They're all, so I'll repeat that. Solazyme, Crossbow, Wind River are all three really different areas of knowledge. How did I know I could work in all of them? I just tend to do that. I tend to dive off the deep end hoping I'll be able to swim. Wind River, I knew what I was doing. It was a consulting business, and I didn't know anything about starting a business, but I knew how to do the engineering because I'd been doing that at Lawrence Berkeley Lab. Crossbow I joined at a board level, and by that time I knew how to be a board member, so I had nothing to do with creating the technology at Crossbow. I was there as a board member, as an early investor, and helped in other ways. Solazyme has been really interesting. They were looking for an investor, so I started talking to them as an investor, and both they and I realized quickly that they needed help at least as much as they needed money. And so they asked me to come on as a chairman, really to help with things like financing and putting, business creation, not really biology, because I'm not a biotech guy. I wanted to learn about it. Let me come back to that in a moment. So they asked me to come on really as a business creation person. Now, as it turned out, I'm doing engineering there because I'm the only engineer in the place. Everybody else are biologists. And we're actually building new kinds of systems. We're growing things and filtering things in new ways. And so I'm soldering wires and writing software and speccing pumps, and it's just all kinds of fun. So I am doing engineering there, but that's not really what I got there to do. I would say that the reason that I wound up at Solazyme is exactly because I wanted to do something different. I'd been at Wind River for 23 years, and when I left there, number one, I was ready for something really different. And number two, I got really interested in biology for two reasons. One, because it's just a really important, I think it's just important to be technically literate in the coming decades to know something about biology, so I got really interested in it. But also because at Wind River we were building really, really complex systems. I mean, these spaceships and some of these huge systems we built, it felt like the engineering, we were really bumping our head against the top of how complex we could actually build something. And so I was trying to learn more about complexity. As soon as you start to think about complexity, you move very quickly to biology because that's where the most complex systems are. We're far more complicated than anything we can build. So I wound up there mostly because I wanted to learn something about that so I could bring something back to engineering and come up with new ways to do software or something like that. But then I wound up meeting the Solazyme guys and got sidetracked. But I don't know, I find I can usually learn the technical part. That's usually the easy part. Yeah.
Do you mind if I ask what the inputs are to your algae?
I don't mind at all, but I can't answer the question. No, the question is, what are the inputs to the algae? And I'm sorry, a lot of this will be, 3 months from now I'll probably be able to answer it, but today I just can't, sorry. Yeah.
Do you see yourself staying in biology for a really long time, or do you see a new domain in the future that you don't being involved with?
Do I see myself in biology for a long time, or do I see myself doing something different? I have no idea. Right now I'm really enjoying Solazyme a lot. I'm learning a lot. I really like learning different things. I wanted to learn. I wanted to learn how you actually work in a biolab. So I did a couple experiments. I spliced some genes, and I quickly learned that I was just in the way in the lab. I was really not helping anybody. But for me, it was great. I learned I learned enough to be literate to have a sense of what's going on in the business. What'll be next? I don't know. At this point, I'm really interested in two things. I'm interested in impacting the world in a positive way. So I'm really not interested in something just because it's going to make money. I might invest in something just because it's going to make money, but I'm not willing to invest my time with that as the only reason. I'm just not interested. And then I'm interested in things where I'm going to learn something, where I'm going to learn something new. When I finished Wind River, I had a lot of opportunities to do something in similar areas. And I'd done it for 25 years. I just didn't need to do it anymore. I was ready for something different, and I don't know what'll happen next. So that's what's fun. And by the way, as my one little bit of career advice is do something you love, and don't be afraid to try something different, and realize now that you're in school that 20 years from now or 30 years from now, you could be doing something really, really, really different than what you're doing in school. And so that's going to come from the base of knowledge that you build up, not just the specifics. It's not going to matter whether you know. I mean, when I built that computer, my portable computer in grad school, I had the part numbers memorized for a quad NAND gate and TTL logic. I knew all that. Well, who cares about that stuff? That stuff's all gone. But the skills you learn about how you conceive of a system and build it, and think about it, and how you think about a problem and solve a problem, those last for your life and are applicable to pretty much anything you do. So anyway, take that for what it's worth. Yeah.
I have a couple of questions about the biodiesel. First, maybe I missed, you said it, how far do you think you're from really having a product that can do some difference? And you said that you have lower carbon dioxide emission, but in diesel there are other aspects of emission that are concerned to the environment. How are you in the other aspects?
Okay, so the two questions are how far are we from actual production of biodiesel, and the second question is diesel has other problems, other kinds of emissions besides carbon, and so how do we deal with that? So how far are we from it? We think we can make thousands of gallons today. We certainly need to make millions. The scale up from here mostly depends on other, not only on the biology and the biotech, but on money, and how fast can you get steel in the ground, how do you capitalize it? It becomes a big capital problem. So I should think we could be in meaningful production as soon as the end of next year, but I would say more likely is 2009. But it's not like 2012 or anything like that. It's soon. In terms of the other issues around biodiesel, diesels haven't been coming into the US, at least diesel cars haven't been coming in for a while, because although diesels are more efficient. You get more gas, you get more mileage, so it puts less CO2 in the atmosphere, but it puts more of other things in, particulates, sulfur, and NOx. And the new diesel engines are much cleaner, and the new diesel fuel is much cleaner. They're about to be approved. So diesels, Mercedes and Audi and a couple other companies will be meeting California emission standards with their new diesels next year. You can already buy diesel cars again in 45 states, but not in California, but they'll be coming back. And by the way, one of the issues, by the way, I don't want to get too, I really don't want to turn this into a technical biodiesel discussion, but one of the issues with the new diesel, the diesel that you buy today in California is low sulfur. It's been mandated, so the fuel is actually different than it used to be. It's a low sulfur diesel. But diesel actually does two things. In a gasoline motor, the gasoline is the fuel, and then there's oil to do the lubrication. In a diesel motor, the diesel oil is not only burned, it's also the lubricant. And the low sulfur diesel is not a very good lubricant. And it turns out that by adding 5 to 10% biodiesel, it becomes much better. So look, is it perfect? No. And you know, my guess is that 20 years from now, we won't be burning anything. But today we've got an entire transportation system which has been built around energy-dense liquids, right? We run on gasoline and diesel, and that's not going to change overnight. It's going to take a long time to change it. So this is an incremental change. It's not perfect, but at least the carbon we put in, we're taking out. So it's carbon neutral, or almost. I mean, you got to transport it and stuff, so there's always energy inputs, but it's almost carbon neutral. And it's pretty clean. So it's not perfect, but it's way better than the alternatives today. My guess is in 20 years it's not what we'll be burning. Do I need to be finished?
Yeah.
Or do I have time for one more?
Time, I think you
Okay.
can approach area closely. Thank you so much.
Thank you.